we just saw that if you only use the x value or the y value to build a binary search tree of two-dimensional objects, you're losing information. And so now what we're going to do is something known as a quad tree, where every node has 4 neighbors corresponding to what I'll call the northwest, northeast, southwest, and southeast. You can also think of that as upper left, upper right, lower left, lower right. So I'm going to show this by demo because I think it's easier to understand if we just build one of these things. And I'll start by saying when we insert A, this is going to be the same example as we had before with one fewer point. So here's A. And let's say we insert A -1, -1. So if we think of this as a BST map, we are associating this point -1, -1 with A. So that is our root, and it has 4 possible children: the northwest, northeast, southwest, and southeast. Okay. So now, if I insert another point, say 2, 2, you might try and figure out what you think will happen next. So 2, 2, that is going to be up here somewhere, so that's going to be in the northeasterly direction. Okay. So we're going to put 2, 2 here, and it will have its own 4 children, okay, which correspond to its northwest, northeast, southwest, southeast. Sorry, northwest, northeast, southwest, southeast. Okay. So next we insert C, which is 0, 1. And so in this case, C, so 0, 1, that's going to be right around here, right? It's over to the right and up a bit. So that's going to be northeast of A, which is already taken by B. So when we go to northeast of A, there's already something there. So now we need to follow one of B's children. Which one? Well, the southwest child of B. Okay. So we go northeast of E, northeast of A, and southwest of B. And the reason we had to actually follow 2 links is because the northeast position of A was already taken. So now, if we were to insert, say, 1, 0, okay, so 1, 0 is also to the northeast of A. That's already taken. 1, 0 is to the southwest of B, and it is to the southeast of C. If we now tried to insert -2, -2, try and figure out what would happen next. So in this case, -2, -2 is to the southwest of A. And unlike our previous examples, that space is currently unused. So we can just put our E here, and there we have our quad tree. Okay, so that's what a quad tree is. We'll see why it's useful soon. However, before we do that, I want to point out that just like a binary search tree, the order in which you insert items will affect the shape or the topology of the quad tree. So if instead I insert D first, it's the root, and then I insert -1, -1, well, A is off to the southwest of D. If we then insert B, which is to the northeast of D, then it will end up here. We'll end up with a slightly bushier looking tree. Next, if we insert -2, -2, well, in that case, -2, -2 is to the southwest of D. That's already taken by A. So then we go southwest of A and end up putting in E. And then lastly, if I insert 0, 1, well, it's going to be in this northwest position. Now these are the exact same points. So if we compare in this demo, well, I can't because I don't have the viewer, but you'll see there's A, B, C, D, and E, and there they are again. So the order in which you insert things will matter, will affect the shape of your tree, to be clear. All right. So what's going on here? Well, here's something really cool. I love this. This is so neat to me. So quad trees are also just spatial partitioning in disguise. So our earlier approach was building these perfect grids of rectangles. That was called uniform partitioning, sometimes informally spatial hashing. In this new approach in quad trees, we actually have hierarchical partitioning, which is just such a beautiful and rich idea. You can make neat art out of it, honestly. So basically each node, it owns 4 subspaces. So A has the top left subspace, the top right, the bottom left, and the bottom right. And how it works is that as you add more and more points, then you can think of space as getting more finely divided in those regions. So over here where there are no points, there's just one big old region, which is the northwest of A. However, on this side where there are more points, we see that we get these relatively fine-grained spaces, where D here owns just these 4 little regions. Okay? And if we compare the 2 different cases, the spatial hashing idea, where we have 25 regions of uniform size, and over here we have 16 regions of varying size, it's cool, it's more intricate. And so what it turns out is that often, not always, but in many circumstances, this approach of breaking your space down into these smaller spaces gives you better runtime than these uniform sizing approaches on the left. Okay. So how do we actually use a quad tree in order to efficiently find, say, the items that interact with a rectangle? Well, I think this video is getting a little long, so I'll stop it here. And in the next video, I'll explain how this rectangle search will work.